In this instructional video, we have a reaction and a value for the equilibrium constant, and we have initial concentration for our reactant and product. What this will show you is how we can use this information to determine the concentrations of our reactant and product at equilibrium, given what we have to start with. So, from the stoichiometry, what we know is that for every 2 moles of NO2 that gets used up, we're going to generate 1 mole of our product, N2O4. And because of that, whatever the change is, it's unknown, so we'll call it X. We know that we can get plus 1X here and minus 2X here. Now I'll be suppressing the units in order to ease writing and explanation of everything. But what we do know then is that our final concentration will be 5 minus 2X for our NO2, and it will simply be X for our N2O4. We can plug this into the equilibrium constant expression, which we know is going to be concentration of N2O4 divided by the square of the concentration of NO2. And we can set that equal to the actual numerical value of 220.2. Now, we expand this out and simplify it. This will give us a quadratic equation, and I have it all written out here to make sure that we get it exactly right. We get 880.8 x squared minus 4404 x plus 5505, and that is equal to x. Now, we want to write this out in standard quadratic formula notation, so we will bring this x to the other side, and that will leave us with minus 4405x plus 5505, all equal to 0. And so now we can use the quadratic formula that x equals negative b plus or minus square root of b squared minus 4ac, and all of this is divided by 2a. And we note that a equals 880.8, b equals negative 4405, and c equals positive 5505. Now, the math of performing the quadratic formula is able to be done using just pencil and paper and a simple 4-function calculator. However, it's not terribly entertaining. So I'll skip to the final answer, which is x equals 2.50057 plus or minus 0.05328. Now, this does not respect all of our rules regarding significant digits, and there's a reason for that. In order to achieve values that we can actually use in the end to compare against the equilibrium constant expression itself, we need to carry this out to a larger number of decimal places than we normally would. Now, if we take the higher solution, what we'll find is that 5 minus 2x will give us a negative value for the concentration of NO2, and that's impossible. So we're going to be using the lower solution, which states that x equals 2.44729. Now, because of how we've written everything, this gives us the concentration of N2O4, and 5 minus twice that will give us the concentration of NO2 at equilibrium. And so our NO2 equilibrium concentration is 0.10542 molar, and for N2O4 it's X, which is 2.44729 molar. And if we take these values and plug them into the equilibrium constant expression, we'll find that we get a value of 220.21, which is sufficiently close to the given value of Kc that we're confident this is correct. So now you've seen how we can take an initial concentration, apply some unknown change, stoichiometrically speaking, use that to determine substitute expressions for the equilibrium amount, develop an equation that can be solved, and ultimately determine equilibrium concentrations given a starting concentration.